Today we're going to go into chapter 20 about organic chemistry, and what the material that we'll be covering today will first of all be hydrocarbons, alcohols and ethers, aldehydes, ketones, carboxylic acids and esters, and amines and amides. There's also a few other things that we'll talk about as well. But one of the main things about organic chemistry that we're going to be talking about is to ensure that you understand how to name the different types of materials. As you know, for all of the different organic materials that we have, there are many, many more of them than there are of anything else. And that's because of the flexibility that we have with the carbon having the possibility of 4 separate places for it to bond, and for carbons to bond to other carbons and just create very, very long chains. So essentially, when we're talking about we're going to first talk about hydrocarbons, and those are ones that involve only carbon and hydrogen, only those two. And they can be saturated. In other words, every single carbon has 4 bonds associated with it. An unsaturated hydrocarbon has carbons that are bonded to other carbons with double or triple bonds. Okay, so we're going to describe the reactions characteristic to them, and we're going to identify structural and geometric isomers of these different ones. Remember, isomers have the same molecular weight, but they have different configurations of the elements making up that molecule. So first of all, just a quick review. We've had methane many, many times, and there are different ways of looking at it. The Lewis type structure, okay, where bonds are replaced by the electrons that are shared for those bonds. You can have the ball and stick model that we've made, and you can also have the spacing model, space filling models that they have down below here. And each one of them, it allows you to understand whether something that can be a straight line or the geometry of the different ones. Actually, once you get beyond 2, it's going to always have to be at least some kinks in that type of structure, right? There's no way you can have it anything other than that. And you can see that the hydrogen are going to be into the plane and out of the plane, as well as on the plane, so that you have 2 in, 1 in, 1 out here, 1 in and 1 out here, 1 in and 1 out here, 1 in and out here, and then these 2 hydrogens are on the same line or the same plane as the carbon molecules. So, and this is methane, ethane, and pentane. So 1 carbon, 2 carbons, etc. Now, because the carbons can have other carbons attached to them, you'd eventually get to a point where you'd have to expand them out like this, right? So that if this carbon right here has a methyl group attached to it, and this one right here has an ethyl group attached to it, it would look like this, and you'd start taking up a lot of space. So what the chemists do is this methyl group, we do it as CH3, and then we have C with 1 H, and then 1 CH3 off of here, and then on down the line like that. Another way of representing that is with this type of a skeletal structure, okay? And the fact that there's not, each one of these means that there's a carbon at each one of those points, and it has many hydrogens as possible on them. This right here, since it's bonded to 2 carbons, is going to only have 2 hydrogens. These on the end will each have 3. Right? This one right here will only have 1. This one right here will only have 1. And this one right here will also have 2. Okay? So you can see how, but this is a lot simpler, but you have to understand what it means in terms of where the different hydrogens and carbons are placed there. Now, here what we have is a molecule, And usually what you do is you base it upon what is the longest chain possible, right? Well, I guess we'll do the names later on. But here, the other ways of representing this and representing this. If it's all in a straight line, it just has an N in front of it. 1, 2, 3, 4, 5, 6, 7. So this would be N-heptane, right? Heptane. Here you have 1, 2, 3, 4, 5, 6, 7. But this doesn't work quite that way. Here you would have the longest straight chain you could have would be these 4 right here. So this is going to automatically be a butane molecule. So it'll be 1 methyl, 2 methyl. I guess the simplest way would be to do it from this side. So it would be 2 dimethyl, 3 methyl butane. Or you could have 2, 2, 3 trimethyl butane would be a way of measuring that. 2, 2. Both of these are on the second one. Okay. I guess here they just want to show how simpler it would be to look at this at those 2 different ones. Well, I guess we'll get to the naming later on, but just keep that in mind. Likewise, when you have ring structures, they would look like this with a carbon off of them. And again, you'd have the same linear ones right here. And these, looking at the stick models, you'd have something that looks like a hexagon with 1 line shooting out from it. And here you'd have just 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 different carbons on this. Here, again, you would have 5 carbons in this ring and 2 carbons off of there. So it would look something like this, right? So you can see how these are simpler, but you have to understand what each one of them means. Likewise with this one right here, there would be 1, 2, 3, 4, 5, okay, with 2 methyl groups off of here, 2 methyl groups off of here. And likewise, here's just another representations of N-butane, and then this would be 2-methyl propane, okay? So that when it's all in a chain, it just takes on the characteristic name that we have for it. If there's anything where it's not in a straight chain, then this methyl group right here, and this is the second one, and you try to get the smallest numbers possible. So this would be on the second carbon, and you'd have 1, 2, 3 here, so this would be a propane, and this would be a methyl group off of the second one. That's why it's 2-methyl propane. And this is just N-butane. These are isomers of each other. But you can see how quite different their names are, and their properties are going to be very different as well. Here, you've got 3 representations of exactly the same thing. So essentially, these actually rotate around these bonds, right? And so this right here, can shift from here down to here, and then this one over here, it's not going to be able to shift up next to it here, but it can shift down from there rather than out on the plane. Okay, so they're not isomers. They all contain the same arrangement of atoms, even though you're just drawing them a little differently. Each one of these has 1, 2, 3, 4 different carbons linked to each other with the maximum saturation each one. So these are like that. Now here's our nomenclature. So this is 1, 2, 3. This is propane. If we put a chlorine off of here, it's called 2-chloropropane. If we have a methyl group off of that one, it becomes 2-methyl propane. Now here you have 1, 2, 3, 6 of them, right? And so you want to get the smallest number. That's why you're going to start counting from this side, because your first substitution is here. If you started counting from this side, it would be a 3, right? Sorry about that. And so this is 2,4-difluorohexane. And here you've got one right on the first group right here, and so you'll start counting from this side. So it's 1 bromo, 3 chlorohexane, right? So understand how it works. Just find the longest chain, and then start from the side which is nearest a substitution in terms of how you assign your numbers. And then if it has more than one, you just identify which carbon something is attached to, right? So yes, 1 chloro, 2 bromo, and this right here has only got 4, so that is butane. So it's 1 chloro, 2 bromo, butane. This next one here, you've got an iodine right here, so you start counting on this one right here. So this is 2 iodo, 3 dibromo, and this is 5 of them right here, pentane, right? 2 iodo, 3 dibromo, pentane is the name for this one. So here's methane, here's the methyl group, here's ethane, here's an ethyl group, and we have other variations on those. Right here, we have 1, 2, 3, 4, 5, 6 this way, and it will only be 5 this way. And so this right here becomes 3, and this right here is ethyl hexane, right? Hexane for this one. This is the 3. This is an ethyl group on here. So it's 3 ethyl hexane for this particular one. Here we're kind of going to, it's the smallest number from here. 1, 2, 3, 4, 5, 6, 7, 8. So this is going to be octane. And then it's going to be 4. And this right here is 1, 2, 3, right? So this right here is going to be propyl. So this is 4 propyl octane, right? 4 propyl octane. This right here is propane, and you have a methyl group here. And so this is 2 methyl propane. And here are some of the different groups. You have the methyl group, the ethyl group, N-propyl, isopropyl when it's into the center one instead of the at the end. This is N-butyl, and this is called sec-butyl, isobutyl, and tert-butyl. Okay, these are just some of the variations that you have for these different alkyl groups that can be substituted onto these. So here we have 7 of them, so that is going to be heptane, and it's, starting from here it's 3, and this is an ethyl group, so this is 3 ethyl heptane. Here, this is your group here. Although these are both on the second ones in, this is the more complex one. So this becomes 2, 2, 4 trimethyl pentane. So each one of these is the same type of group. So you just identify which carbon they are attached to. 2, 2, 4 trimethyl pentane. Here, this is an isopropyl group right here. You've got 7 there, and so that's heptane. And so counting from this side right here, it's going to be 4 isopropyl heptane. And the way in which we get all of our different hydrocarbons is normally by heating crude oil, oil pumped out of the ground, and it goes through a fractionation distillation. So what they do is they have water that they heat up, and then the oil goes, and the water surrounds it, so that they have points on here at which different ones. So the lower boiling materials come off at the different ones. The highest boiling ones, that's your refinery gas. Okay, we'll talk about that in the next section.